AP Cram, Calculus AB, Free Response Exam Review, Question 58, Local Minimums on an Open Interval. Alright, so the figure shows the graph of f prime, the derivative of a twice differentiable function f, on a closed interval where x falls between and includes 0 and 8. Okay? The graph of f prime has horizontal tangent lines at x is equivalent to 1, x is equivalent to 3, and x is equivalent to 5. The areas of the regions between the graph of f prime and the x-axis are labeled in the figure. The function is defined for all real numbers and satisfies f of 8 is equivalent to 4. Alright, so our task is to find all values on x on the open interval x is either greater than 0 or less than 8, for which the function f has a local minimum, and then we have to justify our answer. And the only difference between an open interval as opposed to a closed interval is that a closed interval includes the endpoints 0 and 8, where an open interval doesn't include the endpoints. Okay? So what's the answer, or what are the answers? And it's very easy to recognize the answer immediately, but some people can be misled. So this is easy but tricky at the same time. I'll give you a moment to formulate your answer. Okay, so basically what this question stem is asking us to do is to perform a first derivative test. And the graph of f prime is really convenient because this is just a visual depiction of the first derivative function. So we don't have to do any calculus or mathematical or algebraic manipulation of a function because we're already shown the first derivative. Now, if some people forget that this is the first derivative and they mistake it for a graph of f, they might say, oh, you have a local minimum at x equals 2, or x is equivalent to 5, because you see that these regions are concave up and have minimum values. And although we're told there's horizontal tangent lines located here, these are not what we're looking for. What we're looking for are critical numbers. And critical numbers occur where f prime is equivalent to 0. So the output, or the y value, is equivalent to 0. We have a critical number at x is equivalent to 1. We have a critical number at x is equivalent to 4. And we have a critical number at x is equivalent to 6. Now, some people might say, oh, okay, so we have local minimums at 1, 4, and 6. But a local minimum occurs where the sign changes from negative to positive, because what that means is that on the actual graph of f, let's say that when the derivative is negative, that means the slope is negative. So you might have the function dipping, but then it becomes 0. That means, it's like horizontal, not changing. But then if it becomes positive again, it's taking a turn for an increase. So therefore, you would have a local minimum at the 0 point. All right. So the only place that fits this criteria is when x is equivalent to 6. Okay, because here the graph is going from positive to negative. That means you would end up with a local maximum, something that looks like this in the graph of f. And here it's just going from positive to positive. So I'm not really sure what you end up with right there. But here you have a 0 point that's sandwiched in between a negative region of f prime, and then post the critical point, it's positive. So this right here is our local minimum value. This is our value of x that has a local minimum. So f has a local minimum at x equals 6 because the graph of f prime changes from negative to positive, and based